Hi everyone, welcome back to my videos. I like to do a tutorial on power theorems relating to circles. First theorem is called the chord power theorem. We're given a circle center O. We're given chords A, D, and BC. Remember, chord is a segment joining two distinct points on a circle. We want to prove that length of BE times length of CE is equal to length of AE times length of DE, where E is the intersection point of the two chords, right? Write down what we know, and I'm going to draw segment AB and segment CD because the segment can be drawn between 2 points. Angle BAD is an inscribed angle because its vertex of point A is on the circle and its sides AB and AD are chords. You can use the measure for inscribed angles to get measure of angle BAD equals 1/2 times the measure of arc BD. Angle BCD is also an inscribed angle because its vertex is on the circle at point C and its sides are chords, right? BC is a chord and DC is a chord. And we can use the same formula for measuring inscribed angles. So if we look at statement 5 and statement 7, well, this 1/2 times measure of arc BD appears in both of these equations, right? So we can set them equal, and we get measure of angle BAD equals measure of angle BCD. By the definition of angle congruence, we get angle BAD is congruent to angle BCD. We know vertical angles are congruent, so angle BEA is going to be congruent to angle DEC. By the angle theorem, to statement 9 and statement 10, we obtain triangle BAE is similar to triangle DCE. In similar triangles, measures of corresponding sides are proportional, so we can match up the letters between these two triangles. BE divided by DE is equal to AE divided by CE, and these are lengths. Remember that. We do some algebra, and then we get what we wanted to prove. So theorem 2 is called the tangent secant power theorem. Given a circle center O, tangent segment BA, and secant segment BD, prove that AB squared equals DB times CB. So remember, these are lengths. So write down what we know. I'm going to draw chord AD and chord AC because between 2 points a segment can be drawn and a chord is a segment, right? Angle B is congruent to itself by the reflexive property of congruence. Angle ADC, this angle here, is an inscribed angle because its vertex at point D is on the circle and its sides are chords. AD is a chord and CD is a chord. Angle CAB is a tangent chord angle, right? AB is a tangent and CA is a chord, and its vertex at point A is also on the circle. So we can use measure of angle ADC is equal to 1/2 times the measure of arc AC by the inscribed angle formula, and measure of angle CAB equals 1/2 times the measure of arc AC by the tangent chord angle formula. So you can see these two quantities are equal, so I can set them. So measure of angle ADC equals measure of angle CAB by the property of equalities. Therefore, angle ADC is congruent to angle CAB by the definition of angle congruence. I can use the angle theorem using what I have in 11 and what I have in 5, and I get triangle DAB, this big triangle, is similar to triangle ACB. And make sure that you get the ordering correct so you can do the proportions correctly. So I'll just read out, just the ordering. DB divided by AB equals AB divided by CB. Because in similar triangles, the measures of corresponding sides are proportional. We do some algebra, and then we get AB squared is equal to DB times CB. Okay, so this is the last power theorem. It's the secant power theorem. So given a circle center O, angle R is a secant angle. So I just, I shorthanded it. I mean, I could say RA and RC are both, secant segments, but I think if you just say angle R is a secant angle, that pretty much sums up, the relationship between these two segments. So let's write down what we know. I'm going to draw segment AD, and I'm going to draw segment CB using the fact that a segment can be drawn between 2 points. Angle BAD BAD is an inscribed angle, right? BAD's vertex, this angle's vertex at point A is on the circle, and its sides are chords. BA is a chord, and AD is a chord, right? Measure of angle BAD equals 1/2 times the measure of arc BD. Angle BCD is also an inscribed angle. Its vertex at point C is on the circle, and BC and DC are chords, right? Because they're segments joining two distinct points on the circle. And then we can use the same formula. So we see that we have this common 1/2 times measure of arc BD in statement 5 and statement 7. So measure of angle BAD equals measure of angle BCD. By the definition of angle congruence, we get angle BAD is congruent to angle BCD. I'll use the reflexive property in congruence to get angle R is congruent to itself. And then using the angle-angle theorem with statement 9 and statement 10, we get a triangle RAD is similar to triangle RCB. So I can read off what I have between the two triangles, right? RA divided by RC equals RD divided by RB. And do some algebra, and then we get this relation that we want to prove. So let's do some applications. So example 1, given a circle with center O, length of AV equals 2, length of VD equals 6, and length of BV equals 3. Find the length of VC. So we can just, write, we have a circle with center O in this fact, and then we can use the chord power theorem. AV times VD equals BV times VC. So I know when I did the proof earlier, I kind of reversed the letters. We're not going to be concerned with that when we're dealing with length. So the length of VD is equal to the length of DV. So just so you're clear on that. So anyway, you do some substitution, and we get VC is equal to 4, right? And then we can check it. 3 times 4 is 12, and then 2 times 6 is 12, so it works. Okay, example 2, given a circle center O, BA equals 4 and PB equals 2. Find the length of PC. So we write down what we know, and let's find out what PA is equal to. PA is equal to PB plus BA by the betweenness of segments, and we can just substitute 4 plus 2 is 6, right? So by the tangent secant power theorem, PC squared is equal to PB times PA. So PC is equal to square root of PB times PA. So what is PB? PB is 2 and PA is 6, so we get the square root of 12. Example 3, given a circle center O, PB equals 2, PA equals 6, PD equals 1, and we want to find the length of PC. So we write down what we know, and then we can apply the secant power theorem. PB times PA equals PD times PC. So we substitute, and we get PC is equal to 4. So let's work on problem 1. We're given a satellite orbits 200 kilometers above the Earth's surface. So AB equals 200 kilometers. So A can be like the satellite, and B can be a point below on the surface of the Earth, right? The diameter of the Earth is equal to 1,300 kilometers. So BC equals 13,000 kilometers, right? And the satellite sends a signal to Earth. Find the range of the signal needed to reach the horizon at point D. So write down what we know, and we know that segment AD is a tangent segment, right? So by the betweenness property of segments, segment AC equals segment AB plus segment BC. So segment AC equals 200 plus 13,000, so that's 13,200 kilometers, right? AD squared equals AB times AC by the secant tangent power theorem. And then AD equals square root of, what is that, 200 times 13,200, and that's going to be about 1,624 kilometers. So that's about how long, that's the range you need on the satellite to reach the point D. So the next problem's challenging. There's actually a direct application to physics or engineering. So this is a geometry problem, but you can kind of think of it as kind of representing a physics problem. So like think of a wheel that's up against like a curb, right? And it tries to, it's T is like the curb point and it's stuck there. It can't go over it. So, if you know some physics and engineering, you gotta do torques and all that rotation stuff. So anyway, we're not going to get into any kind of physics or engineering in this problem. We're just going to solve it from a geometry standpoint, and we're going to determine the diameter of this circle. So we're given a circle center O. Length of segment ST is equal to 10, and ST is not a tangent line, so the tangent line would actually have to be like over here. You can see it's not a tangent, so that's going to be extremely important in this problem. RS, the length of RS equals 15, but segment or line RS is actually a tangent line. Segment TS is perpendicular to line SR. So let's find the diameter of the circle. We're going to write down what we know, and we're going to draw a line through point R that's parallel to segment ST. So we can do this by the parallel line postulate, right? And then we're going to pick a point I such that the distance from point R to point I, and I is on this line here, is going to be equal to the distance from point S to point T. So, okay, so now we have this point I. So we know that line IR, so if we draw this line here, right, we know it's going to be perpendicular to this tangent line SR, right? Because if one of two parallel lines is perpendicular to the third line, then the other line is also perpendicular to the third line. So how do we know that? Well, we know that TS is perpendicular to this line, right? We're given that. And we know that these two lines are parallel, so this line has to be perpendicular to this line RS. We know that line IR, if we extend it, it passes through the center of the circle, point O, right? Because the tangent line is perpendicular to a radius at a point of tangency. So I know we're dealing with a line, but if we just took this segment RO, which is just a subset of the entire line, right, this would be the radius, right? So, we know that this line is going to go through the center of the circle. Okay, we're just going to have to accept this without proof because this would take too long, and it would, I think it would kind of detract from the actual problem. We'll just accept that ITRS is a rectangle. I mean, we can prove that if you want. You can try that on your own, but I'm just going to accept it without proof for right now. So segment IR is congruent to segment TS, and segment IT is congruent to segment RS because opposite sides of a rectangle are congruent. So by the definition of segment congruence and by substitution, we get IR equals TS equals 10 and IT equals RS equals 15. Now we know that a radius that is perpendicular to a chord bisects the chord. So this radius OR, right, it's going to bisect this chord UT, right? Where we've drawn this, I guess you can draw this, extend this line as segment IT to the opposite side where it reaches U. But anyway, let's keep things kind of simple. We don't have to overcomplicate things and just say that segment UI is congruent to segment TI. So we know the length of UI is going to be equal to the length of TI because of the definition of segment congruence. And we get UI is equal to TI, and we know that TI is equal to 15, right? IT is equal to TI, which is equal to 15. So we get this relation. So now we can use the chord power theorem. We can use chord UT and chord AR. So length of AI times length of IR equals length of UI times length of IT. So if we do some substitution, we know that we're trying to find AI. So we know IR equals 10, UI equals 15, and IT is also 15. So if you substitute, you get AI equals 22.5. So what is the diameter going to be? Well, we know AI equals 22.5, right? And we know that IR equals 10. So you just add these two quantities together to get the full diameter. You can use the betweenness property of segments, I guess, to justify that. So length of AR equals 22.5 plus 10 equals 32.5. So if you want the radius, you just divide it by 2. So that's like 16.25. So that would give you OT, for example, like the distance between the curve and the center of the circle. And you can do some more cool stuff based off of that. So here's another challenging problem, and this problem looks kind of weird, but I think it's an interesting problem. So given triangle ABC is equilateral, and we have these circles that are inside this, and they touch each other, and they touch the sides of this triangle, and each circle has radius 10, and we want to find the length of segment AB. So I thought about this, and how could I relate this to a real world problem? So what I thought about is I thought about a boat that's floating in the water, and you stuff, you place these logs, that have like a circular cross section, and then you kind of stack them up like that so they fit inside the boat. And you could figure out doing this. I don't do this in this formula, but you could figure out how many logs you could fit in the boat, based off of this schematic. But we're just going to do something simple. We're just going to calculate the length of AB based off of this arrangement. But you can do other cool things. I thought it was a pretty interesting brain teaser kind of thing. So let's write down what we know. Okay, we know this is an equilateral triangle, so the measure of angle A is going to be 60 degrees, right? And the measure of angle B is going to be 60 degrees because the measure of each angle of an equilateral triangle is 60 degrees. So if you look, segment AR is a tangent segment, and segment AS is a tangent segment. So we saw in an earlier video the two tangents theorem. So segment AR is congruent to segment AS. And what we're going to do is we're going to take segment AW is congruent to itself. And what I'm skipping over here, but actually I'm not skipping it. I'm actually going to details. Never mind. Okay, so segment WR is perpendicular to segment AR, right? Because WR is a radius and AR is a tangent segment. So we know that the radius is going to be perpendicular to the tangent segment. And we know that segment WS is perpendicular to segment AS. Okay, so the measure of angle WRA, this angle here, is going to be 90 degrees. So we know that triangle ARW and triangle ASW are right triangles. You can also show that this measure of this angle is going to be 90 degrees. I didn't do that, but you could do that as well. Same reasoning. And that's because the triangle for a right triangle is a right triangle. So we can use the hypotenuse leg postulate to show that triangle ARW is congruent to triangle ASW, right? With AW being the hypotenuse of both triangles. And we know that length of AR equals length of AS, so that's going to be the leg. So anyway, we prove this congruence, and therefore angle RAW is congruent to angle SAW. So remember, if you remember the definition of bisection of an angle, it splits it into two congruent parts, right? So that's what this AW, if you take this as a ray, it's dividing this big angle into two congruent angles. So the measure of each of these smaller angles is going to be 1/2 of the larger angle, right? So that means the measure of angle RAW is going to be 1/2 times the measure of angle A. And we know the measure of angle A equals 60, so this is going to be 30 degrees. So this is going to be 30, this is going to be 90, so, if we sum, the sum of all angle measures of a triangle is 180 degrees. So this measure of angle AWR is 60. Well, now we have a 30, 60, 90 triangle. We know how to work with those, right? So we know that WR is a radius, so its length is 10. So we have this special ratio, right? 1 square root of 3 and then like 2. So we know that the length of AR is going to be 10 times square root of 3. So we know AR is already this quantity. So now we have to know what RT is. So I'm not going to go into detail with this. So just look from the figure and, we can just kind of accept that this is a rectangle. I'm not going to include the proof. So RT is going to be, the length of RT is going to be equal to the length of WY. And, we can just add these radius together. There's 1, 2, 3, 4 radii, because all these circles have the same radius. And what's 4 times 10? It's going to be 40. So the length of WY is going to be equal to 40. And because this thing's a rectangle and these two sides are congruent, the length of RT is going to be 40. You can prove that if you want. We'll just keep it simple for this. TB, we can use the same reasoning, the exact same reasoning as where we derived that AR, length of AR is equal to 10 times square root of 3, and it's going to be the same thing. BT, or length of TB, is going to be 10 times the square root of 3. We'd have to do the same reasoning, and I don't want to repeat this because that's going to make it too long, but just follow the same types of reasoning as we did to derive that length of AR is equal to 10 times square root of 3, and just do that with angle B and so on and so forth. So length of AB equals AR plus RT plus TB, where these are all lengths, right? So if you add it together, we get 40 plus 20 times the square root of 3, and that's going to be the length of segment AB. So that's the end of this video. I hope you enjoyed it, and I thought these problems were pretty interesting, and they have some relevance to the real world, and they're definitely challenging problems, but kind of go over them, and it might help you if you're in physics or engineering and you do, I don't know, stuff related to this. I don't know how this, maybe if you wanted to optimize the shape of something that holds kind of these circular type objects, you could do that. So like I said, that's all I have for you tonight, and I want to thank you for watching my videos. I want to wish everyone a good night, and I hope to see you during my next tutorial. All right, take care everyone, have a good night.